IGAFIT colloquium. So we have a pleasure of having with us Sergei Vassilvitskii. He is a research scientist at Google in New York, and he has been previously at Yahoo Research. He did PhD at Stanford in 2007 with Rajiv Motwani. And I'm assuming all of you have already seen many papers of him, or you are familiar with his amazing research in clustering, indexing, MapReduce, and most recently in learning-augmented algorithms. So Sergei will give a talk in a second, and before I will just give him the floor, let me just tell you that if you have any questions, please ask them on a chat. I will be following the chat, and then I will just read it to Sergei. And other than that, Sergei, yes, please go
on. Thanks, Arthur, and thanks everyone for joining at a slightly different time. We're working with time zones best we can. The good news is that I'm not jet lagged. So we'll see how this goes. And it's nice to see a lot of familiar faces who I haven't seen in many months with this pandemic on the call. So let's begin. As Arthur said, the talk today is about this kind of relatively new area of algorithms with predictions. And the best way to describe it is actually through a very simple motivating example to get us all on the same page. So let's think back to algorithms 101, right? You're given a sorted array of integers, 1 through n. Here it is, 2 through 98. And I give you a query, the number 7, and I ask you to check, is the query in the array? Right? And of course, we all know how to do this. This is our bread and butter, right? We do binary search, we look in the middle, we know that the array is sorted. We're gonna say, well, it's less than 44. Recurse on the left half, it's less than 11. Well, it's more than 4, it's 7, et cetera, right? All of this is very familiar. What is our running time? Our running time here is logarithmic in the length of the array, right? So this is really as algorithms 101 as it gets. Now, why am I talking about this? Suppose that somebody gave you, in addition, some prediction of where the query should appear. And the way to think about it here in this example is you say, well, I have this sorted array. Maybe I know that the numbers are between 1 and 100. And so if I'm looking for 7, it's likely that it's going to be sort of towards the earlier part of the list rather than in the end. And so what am I going to do? I'm going to start my search not in the middle, as we do usually, but wherever this prediction tells me that I should go. Right, and so if I say 7, maybe the prediction says, well, look over here in the 6th coordinate instead of looking in the very middle of the array. And now we do what you would do otherwise, right? We know that the array is sorted, so I started with 22. Instead of recursing on the full half, I'm going to do doubling binary search, right? So I'm going to look 1 away, then I'm going to look 2 away, and here I found it. But if I hadn't found 7 right off the bat, I can then go and continue this doubling until I go too far, and then do standard binary search afterwards, right? So again, this is really simple. If you have a bunch of books on the bookshelf and they're in alphabetical order, this is what you would actually do, right? If you're looking for, Arthur's books, you're not going to go in the very middle of the bookshelf. You're going to go towards the beginning and start from there, right? The analysis here is also really simple. Right, so I'm going to define as eta my error measure, where here is just going to be the L1 distance between where my prediction said that the number 7 should appear and where it actually appeared, right? And so eta here is 4. And it's very easy to convince yourself that the running time of this little method is going to be logarithmic now, not in n, but logarithmic in this error measure. The amazing thing here, right, this is not very deep conceptually. The amazing thing here is that you can actually train such predictors and you see performance wins. And I tell you that this is amazing because the evaluation of the prediction also takes some time. And we know that binary search is super fast. It's been optimized to oblivion over the last, 70 years, right? And so the fact that we can actually speed this up on large enough arrays is a nice thing to have. Right? So now if I were to take, and so this whole area is kind of looking at predictions and saying, how can such simple predictions help algorithm design? And why? Oh, right, just a little bit on the analysis. Of course, classical is log n, but predictions is log of eta. Here, it actually, immediately you have two very nice properties that follow out further. If your predictions are perfect, right, if you're given really the true oracle, you get constant lookup times. And this is as good as you can possibly hope for. But they're robust as well. Even if your predictions are terrible here, you're not going to do too much worse than the classical algorithm. Here, you're going to lose a factor of 2, maybe it's a factor of 3, depending on the details, but it's on the same ballpark. It's not that you're really relying on the predictions, and if they're, for some reason, are terrible, you're way out and you take a linear time or something like that, right? And so the area has grown to say, you know, how do we tie performance of the algorithms to the quality of the predictor that we have? And you're kind of reducing algorithms to machine learning a little bit, right? But there's still that algorithmic aspect in the reduction. And if somebody, you know, your favorite machine learning researcher comes back and says, I have this amazing system and can predict everything, you say, great, I'll just plug it in, right? And now I get a better algorithm as an outcome. Why is this interesting? So, of course, I mean, it started as an interesting aspect of how do we use learning. But if we take a little bit of a step back, not too far, it's kind of understanding of how we go beyond worst case analysis of algorithms, right? And of course, worst case analysis is our bread and butter. We know very well how to do it. We have good reasons for doing it because usually we don't know much about the distribution that comes in. But sometimes worst case is a little too worst case. And the lower bounds seem often simple, and yet you can't do anything about them. So what do we do next? And so there's multiple ways that we've all seen also in the literature, right? You can start assuming that your input is stochastic, that it's drawn from some distribution, and you say, well, maybe I know the distribution, maybe I don't know the distribution. What do I do then? So it's still worst case over the set of distributions, but then I have some other structure on the input. Random arrival is, you know, I think my favorite one, or the easiest one to see, that we see all the time. We assume that the elements arrive in random order. Can you actually test that? Of course not, right? But it's some assumption that gives you some hold on saying, well, I can go beyond and break the lower bound that has no assumptions at all. Instead of random arrival, maybe you see some samples from the input, some random samples before, and then the rest of the distribution is worst case. And there's been also a line of work on what I call optimistic analysis, where you say, I suppose I think this is the distribution, or this is the set of the family of examples that I'm going to see, and I'm going to be optimistic and react as if the items are coming from this family. But in some case, I'm going to do trust and verify. And I'm going to say, well, but if it's not, I'm going to fall back to the worst case option. And so if I'm correct about my guess about the family of instances, then I do as well as I can on the family. And if I'm not, I'm still kind of in the worst case setting. So all of these have a rich literature behind them that dates back decades. And the question that I want to ask today is, you know, in all of these cases, we're adding some structure on the input. And it's that structure that allows us to go beyond the worst case analysis and say, there's something better that we can do. Right? Is there a way for us to unify a lot of these models and to say, here's one way to think about all of this structure, and it's really different views on the same thing? And then I can say, well, it's maybe, you know, maybe I'm assuming stochastic input, maybe I'm assuming random arrival, or maybe I'm assuming the existence of these predictions. All of these give me something new to know about my instance. How do I use it? Right? And how do I do this in one fell swoop instead of specifying the analysis to say, well, I have one submission on stochastic input and another paper on random arrival and another paper on something else, just because we don't know how to combine it all. So today, kind of this is the intro. I'm going to talk about two results based on two papers. The first is exactly in this latter sense of using predictions as a unifying lens. And here we're going to look at the, again, classic secretaries problem and say, okay, for secretaries, all of these variants have been well studied. How do we unify this? And this is joint work with Paul Duding, Silvia Lattanzi, Renato Paisleme, and that's going to appear in EC. And then the second one, we're going to switch a little bit and say there's been a lot of work on using predictions to improve competitive ratios in online algorithms, and it's natural to see why. But can we go back and say, how do we make things faster? How do we use predictions to actually improve the running times of the algorithms that we have? Okay, so let's jump in. So predictions as a little bit of a unifying lens. If you have questions on the setup and just sort of the main theme, now is a good time. So secretary problem. We've all seen it. It's either really early in the day, or it's late in the day, or it's in the middle of the night. So what is the problem that we have to be on the same page? We have n candidates that are going to arrive one at a time. And we're going to assume that they're arriving in a uniformly random order. Right? Every time a candidate arrives, we say, well, here's a candidate. They are either the best one that's hired so far, that we've seen so far, or they're not the best person. And we have to make a decision right then and there. Do we stop our search and we say we're going to hire this person? Or do we say, well, you know, this person is good, but there maybe we're going to wait for something better, and we're going to wait longer, right? And this is an irrevocable decision. So once you pass on someone, they are very upset and disappointed with you. You will never see them again. The goal is simple. It's just to hire the best candidate. Second best gives you absolutely nothing in this setting. This was the very first interview question that I've gotten, like way back in the day, was, here's the setup. I didn't know anything about the problem. Here's the setup. How would you solve it, right? We all now, of course, I think all of us here know the solution is you wait for some fraction of time. You see your first N over E interviews, where E is the 2.71828. And then you say, this gives you some sense of the distribution of how well people are doing and so on. And then you're going to hire the very first candidate who's better than the first N over E that you really almost sacrifice to get a sense of where these candidates are coming from. Right? And it's easy to prove, again, that the probability of success here is 1 over E. And this is the best trade-off that you can achieve. Classic problem, lots of different proofs, lots of different solutions. Now, if I do a learning variant and I say, okay, well, how can I go beyond 1 over E? I can say, well, maybe somebody tells me, you know, something additional. So I get a noisy oracle that says, is this candidate the best one you're going to see or not? Now, this noisy oracle might come in the shape of a recommendation letter, if you want to think about it this way, where somebody writes and says, this is the best person on the market this year, right? They may or may not be correct. And so I see this for every candidate that's arriving. How do I solve this problem? Right? What do I do? What kind of solution am I going to have? So instead of looking at learning for now, I'm going to look at other variants. And these variants follow this beyond worst case framework that I talked about before. All of them make an additional just modeling choice that say each candidate comes with a quality. I'm going to call it Q, and higher quality is better. Right? Now, this quality is unitless, so it's just something to give us a total order, really, on things. And now I can have different secretary variants. I can say, well, suppose these qualities are drawn IID from some fixed known distribution. So let's even say that the distribution is 0, 1 uniform. Right? It's a very simple distribution. And so I get these qualities, and I see somebody who's a 0.3. And so if I see somebody who's a 0.3, if it's early in the time, I'm going to say, well, I'm going to wait longer. And then I see somebody who's 0.8, but I know I only have 4 candidates left. Am I going to risk it and say, like, I'm going to get something better later on, or am I going to keep it? And these are the kinds of, this is the kind of way that, kind of setup that's been studied for the secretary problem as well. And you get, Gilbert Moseller showed that you can get much, much better. You can get like 0.55-ish. In terms of a competitive ratio. If you don't like distributional, let's say that they're IID, you can say, well, maybe the quality follows some Markovian process, right? So here, for example, I'm going to say the quality of the next candidate is just some random perturbation, random walk on the previous candidate that was there. So all of the other ones don't matter. And so this is, I have some walk that's going on here. Again, it's an optimal stopping time question. There's a recent line of work that's really nice that says, well, you know, knowing the full distribution is a little bit unreasonable. Suppose you have K samples from this distribution, right? And so the way this usually goes is that somebody adversarially, I select k plus n qualities. The algorithm is going to see a random subset of k initially, right? And now I run the same secretary problem again, right? And so I have a little bit of randomness. And all of these things are capturing just different ways that I can relax the problem to go beyond the 1 over e. Because in the end, 1 over e is not, it's great, it's constant, but it's not that great. And we can always do better. So all of these are some sort of advice over the worst case guarantee, right? And learning is just yet another variant here. And all of these have their own kind of worked out schemes on how do we prove optimality and what is the right solution that's going to be. So I want to take this and say, well, is there a common model for all of these, right? And can we use this common model to capture something interesting? So here's a very simple common model here. So I'm going to look at ranks. I'm going to say let R1 through Rn just be a permutation of 1 through n. And so each Ri is just the rank of the secretary, the rank of the candidate that I'm seeing. Maybe higher is better. This is just regular secretaries. How am I modeling a device? I'm going to say there's an abstract signal, Si, that comes from some space S. And the tuple of all the ranks and all the signals is drawn from some known joint distribution. And now what is that known joint distribution is going to be different for different variants of the problems. But what am I seeing is that the algorithm is going to observe the signal. This is the advice that comes in, the recommendation letter that comes in with every candidate, right? And of course, the algorithm, as before, knows the relative order among the people that they've seen already. So the relative order of R1 through Ri. And now, given that you know the joint distribution that these were drawn from, and you know the signal that you're seeing right now and the relative order, how well can you do? And what is the strategy that you should employ? So how does this model the variance that we've had? So distributional one is the simplest one. Right? SIs, these signals are just exactly the draws of the qualities that we had from the distribution. And the ranks are going to be the induced ranks on the signal. So the way I'm going to do the joint distribution. I'm going to say, first you draw the signals. Then you look at which position is the highest one. That one is rank n. The next position is rank n minus 1, and so on and so forth. And this is the joint distribution between signals and ranks, right? And now you proceed as before. In the Markovian setting, it's also simple, right? I'm also going to do this induced ranks to generate the RIs, but the signals themselves are not independently drawn. They follow this Markovian Markov walk, right? In the samples, it's a little bit trickier to define, but really, again, not that hard. It's to say, well, what is the signal? The signal is going to be the rank out of the k samples known to the algorithm. Right? So I'm going to say, well, here's, again, I drew the k plus n qualities, or they were given to me adversarially. Somebody's decided which k, this is the distributional part, which k are going to be given to the algorithm. And now the signal for each additional person coming in is the rank among those k that you have, right? Because that's really all you know going forward. And the way that we're going to model learning here is, again, we're going to say, well, the probability of a signal saying that this is the best person, given that these are the best ranked, is going to be p. And the probability that the signal is that this is not the best person, given that they're not, is also going to be p. We can change them to be different, but this is just for simplicity, right? And so all of these variants fall into this framework, and I can express it to say, really, it's just a joint distribution on signals and ranks. But in some sense, I haven't really done all that much yet. Great. So now let's look and say, well, these are the variants. What do the solutions look like to all of these? And there's really, if you explore, there's really two kinds of solution concepts that we see, because these are almost the most natural and the ones that you would expect to see. We're going to call them memoryless and threshold policies. So what is memoryless? Memoryless just says the decision that I'm making depends just on the ith candidate that I'm seeing and the signal that has come from them. I don't care about the signals that I saw before, because this is how they were generated, right? I just need to say, okay, for this candidate, are they the best one so far? If not, obviously I should reject them. because they're not going to be top overall. If they're the best ones so far, great, what is their signal? And based on that, I'm going to say accept or reject. I'm not going to look at anything else. And this is efficient to implement, of course, because I don't need to store all of the signals that I've seen before. My acceptance rule is relatively simple, and all of the policies that we've seen follow this. I can go even one step further. And again, this is almost what you would expect to see in your head, right? And we're going to call these threshold policies that say, not only is it this way, but it's also monotone in the following way. For every signal, there is a time starting at which you're going to say, this is good enough for me, right? If we look back to the Gilbert-Mosteller distributional variant, what does it say? Again, suppose everything is drawn from 0, 1. I'm going to say, OK, once I see a candidate whose signal is 0.8, at some point, this is going to be good enough. I'm not going to say accept. If I saw this candidate later on, I will accept them then as well, because it only makes it, I only have kind of less shots at the apple, less bites at the apple, less shots at hiring somebody even better later on, right? And so really here now for the policy, the decision is to say for every signal, there's a time. And if you see somebody after that time who's the best one so far, you're going to take them. All of the previous variants that I talked about have the optimum policy, and this has been painstakingly proven, are threshold policies, right? So for instance, just to get on the same page, for the classic secretary problem, we just have a single threshold. There's no signals, right? And there's a single threshold at N over E. You don't hire anybody before N over E. Anybody after N over E, if they're the best person so far, you're going to hire them. For the Gilbert-Mosteller variant, this is distributional. Again, you have thresholds, but now they depend on the signal. You're going to say, OK, if it's 0.8, I'm going to start hiring them starting at, I don't know, 3/4 of N or something like that, right? And it's the exact trade-off that you can figure out. So why? Is this a coincidence that all of these have the same optimal policies? No, otherwise I wouldn't be telling you about this, right? So we just need a tiny little bit more of notation, right? So I'm going to use just a squiggly less than to say this is the partial order induced on the first I elements. And I'm going to use Ti as this event that I is the best element so far. Because of course, you only stop if you are the best element so far. Your goal is to find the best overall. If you stop at any other time, you can do strictly better by not stopping then, right? Or at least as well. Okay. So now, what is it that we have left to play with? I said, well, there's this joint distribution on signals and ranks. Right? And now we're going to say, well, let's have some properties of that joint distribution. And we're going to have two properties. One is non-filtering, one is history of relevance. They're somewhat technical, yet they're pretty simple to explain. So I'm going to skip here to the last line of the slide, right? And I'm going to say, well, actually, let me not skip. Let me say, what is it that we're looking at? Let's skip the first formulation. I'm going through, and I'm now at sums element J. This is the green element at 11. It has the signal 11. And this is the best element that I've seen so far. Now, this gives me some conditional distribution that this is the best element overall, some probability. Later on, suppose we say, no, we're going to keep going. We get another element with signal I. That's also the best so far. The fact that I arrives later doesn't really change what we knew about J. Sort of the signal that we see with I doesn't really change what we could have learned about it then. Once the information set remains the same, right? And so the future doesn't really affect there's enough independence so that the future doesn't really affect what we're doing. Right? History of relevance goes the other way. We're going to say conditioned on the fact that right now you're at the top and the signal is the best that it is, right? The information that you have available at your time and the fact that this is the best element so far are independent. So again, the past performance, which you've seen in the past, right? And this is almost kind of the definition that we had of memoryless policies, right? This is exactly what you need. everything that you need is there, the fact that this is the best element so far, and this is the signal that you're seeing. So this is just a formal way of saying that. So now we come to the main result that says, well, for signal structures that satisfy both of these, the optimal policy is memoryless, right? And this is a single proof. And so now what you want to do if you have a new variant, you just want to say, well, if I model it appropriately, this joint distribution on signals and ranks does satisfy these two properties. How do we prove something like this? I'm not going to give you the full proof here. I'm not even going to give you a sketch. I'm going to give you a strategy. So there's a beautiful paper on the secretary problem that says one way to solve the secretary problem is by writing down a factor revealing LP. So this is by Bhujbal, Jain, and Singh. And they say, here's a factor revealing LP. And this LP actually fully captures all of the policies, all of the stopping policies that you can have for the secretary problem. There's a one-to-one mapping between the solution to the LP and what you could possibly do, right? And so what we're doing here is that we can say, well, let's take this LP and let's augment this with a signaling structure that we have. And we can show that under the two assumptions that we have again, the solutions to the LP, like first, there's still the one-to-one mapping between LP solutions and policies. And we can say that all of the solutions are actually memoryless. And so this then allows us to conclude that for the signal structures that satisfy these two properties, the optimal solution is memoryless as well, right? And this captures all of the variants that we talked about. The second result is, how do we go from memoryless to thresholds? Now we have this LP, we can look at its dual, and we can say, well, can the dual be solved greedily, really by backwards induction? If I go in a lot of these properties, in a lot of these variants, it's very easy to say, if this is the very last element that I'm seeing, what should I do? That's easy. If this is the second to last element that I'm seeing, well, I have a good idea of the distribution of the last one. And so now I can do this trade-off of saying, well, is it likely that it's going to be better than what I'm seeing right now? Right? And so you do backwards induction. And this is how a lot of these proofs proceed. And then we say, if this is how you can actually solve the optimum for the LP, with a tiny technical asterisk there, then the resulting policy is a threshold policy. So now you can say, okay, I have a new variant that I want to solve. Here's the signal structure. Does it satisfy an F and HI? If it does, great. At least I know that it's memoryless. The only thing that I need to look at is the signal at a particular time. And now I can also write down the LP and say, can I solve this just using backwards induction? Can I prove that that's the optimal solution via usually complementary slackness? And if you can, then you're done, right? And now you can say, here's the LP. The LP gives me these thresholds for every signal that I have. And this is the optimal solution that I need. And what we show in the work is to say, let's take all of these past papers, and we can derive and show that this is true, and we can actually derive the solution to the LP in somewhat closed form for all of these. So this is kind of the formalism. I want to go back to the problem we started with, which was the actual learning problem, just to see what does this look like, right? So again, remember what our problem was. We said, assume we're doing in the regular secretary problem. Let's assume the existence of an oracle that gives a noisy signal on whether this candidate is the best candidate, right? And the way that it's going to be noisy, it's going to be correct with probability P. And here, just for simplicity, I'm going to assume that this is symmetric, right? That the noise is symmetric on the best elements, the best candidate that arrives, and the non-best candidates that arrive. You can twiddle these, everything still works out. Right, so formally, again, I'm going to say that the signal that this is the best candidate, given that they're the best, the probability of that signal appearing is P. The probability the other way is also P. So now P is at least a half, because if P is less than a half, I should just look at the opposite, what it's telling me. And now the optimal policy we can conclude as a threshold policy. So what does this mean? There's going to be, what is the optimal solution is going to look like? There's going to be two thresholds. Before the first one, you don't accept any candidates, right? You're still trying to learn and see kind of what does your space look like, regardless of the signal. For between the two thresholds, you're going to say, well, if my oracle tells me that they're the best possible, I'm going to accept them if they look to be the best so far, right? And then in the end, you say, well, forget about the oracle. Maybe it's wrong. Maybe it's something else. I'm running out of time. Regardless of what the oracle is telling me, I'm going to accept the best person I've seen so far, right? And so if you think about the classic problem that we have, both of these thresholds are the same. Right? And what the oracle allows you to do is to really reduce one of them, so you start accepting a little bit earlier, right? And you also delay the other one, so you're less likely to be fooled by sort of, number 3 coming in, or what is it? Number 2 coming in after number 3, but before number 1. Right? So this is an example where you would be fooled in the usual setting, but here, if the oracle is correct, you get a little bit more, and you're going to say, well, maybe not. We can compute the thresholds, but it's easier to look at pictures. So here they're just labeled threshold yes and threshold no. So there are 2 plots here. On the left-hand side, we see the competitive ratio and how it evolves from 1 over e when the oracle carries no information at p equals 1/2 towards 1 when the oracle is always perfect. So we always know those 2 endpoints, this is what they should be. And the question here is, what does that curve look like, right? As you get a better and better solution, how much do you gain in the competitive ratio? And the plot on the right is showing exactly the evolution of these 2 thresholds, right? So the red line is the threshold when the oracle says, yes, this is the best one. So it gets earlier and earlier. So if your oracle is reasonably good and you say, okay, now I'm going to see something, I reduce the time where I'm relying on this is the best so far signal, and I'm using more of the oracle signal to help me decide, right? And at the same time, I'm saying, well, I'm trusting more and more in the oracle as p grows towards 1, and so that's why the blue line goes closer and closer towards n, that I'm not going to accept somebody where the oracle doesn't say that they're the best person so far, right? And so you have this evolution. It happens. And we know by the analysis that we've done before that this is actually optimal for this case. So to conclude here a little bit, so what was our starting point here and what have we done? We said there's a line of work on predictions and learning, and we can actually find the right level of abstraction to have one formulation to capture all of these different variants. And in some sense, this is really nice because we shouldn't have very different proof ideas to say, well, are these samples drawn from a distribution? And we know the full distribution support, or do we just have a few samples and the rest is adversarial? Or there's something else going on, we have some help here. All of these are capturing the intuition that says we know something extra about the problem that we have, right? And so here, what this allows us to do is to discover really necessary and sufficient conditions, these minimal requirements on the signals that tell us this is the solution space, right? And so one example where things don't work, because this will be interesting, is to say, if your writers don't say, you know, this is the best person in the pool or not, but they say they are top 10, then not top 10%, top 10% goes through, but if they say they're top 10, period, right? This is something that we can actually show violates these non-filtering history of relevance assumptions, right? And there, if you actually trust this signal completely, what you should do is you should run the regular secretary algorithm just on the places where people are in the top 10. Right? So you now reduce your pool to 10 people, essentially, and this is all you need to do. And this is not memoryless. So extending this kind of analysis to capture richer advice, right? This top 10 advice is very natural, right? Like this is what a lot of the reference letters ask you to fill out. You know, are they top 1, top 5, top 10 of the people you've ever worked with, or something like that, right? But that particular one doesn't fall into this category. What we have. So it'd be nice to extend it further. So that's all I'll talk about secretaries. So this is a different line of work with Mike Dinnett, Sung Jin, Thomas Losita and Ben Mosley, which will be on archive as soon as we finish it up.
There is one question
yes.
by Robbie. Is it crucial to know P exactly?
It is, unfortunately. So in this formulation, you do need to know P exactly, but of course, if you have a lower bound on P, that's kind of good enough. And the thing that's interesting here is that if it's symmetric, the number of events where you get to observe what the oracle says versus the number of events where you care what they say is vastly different, right? Because the number of events where top I is going to be hit is roughly logarithmic in the size under random arrivals, right? But the number of events where you actually see whether the oracle says they're the best so far is not. So you can actually reasonably, assuming symmetry, you can reasonably estimate the quality of your oracle by saying on all of the events where I know this is not the best person because I've seen somebody better before, what fraction of the time did the oracle actually tell me that they're the best person? These are kind of training evaluation points that you get for free. And so you can get some sense into the quality there. Okay, so now using predictions. Now, if you take if you think about it and you say, okay, I'm an algorithms designer, and now somebody tells me that I have machine learning predictions that are going to tell me something about my input, where should I use this? Right? And you open up your favorite algorithms book, whether it's CLRS or Climate Retardos or something else, and you say, well, aha, online algorithms are the best fit here, right? Because what are online algorithms? They're dealing about uncertainty that's coming into the future. I'm dealing with the worst case, and here now I know something about what's going to come in the future, so everything's great, right? And there's been a flurry of work on different directions in online algorithms. We just talked about secretaries. There's a rich line of work now on caching, metrical tax systems. You can capture ski rental, really simple kind of online choices. You can look at scheduling. Like a lot of online scheduling has strong lower bounds for reasons that are relatively brittle, right? You're either kind of in this world or you're in this totally other world, and you can't be in both. And if the prediction just tells you which world you're in, you're instantly violating you can break through all of the lower bounds, and so you can do something better. Online learning, more in almost a regret setting, there's been some nice work. So it's really a natural fit. But what about the original formulation? The example that I started with had nothing to do about online learning, had nothing to do about online algorithms. It just said, here's my binary search, and I can speed it up if I know something about the instance or the data structures that I have. Right? So can we replicate that elsewhere? Right? And what we're going to look at is what's really known as warm start. So if you look at large problems that are actually expensive to solve, it's rare that you solve them once and then you go away. Right? Usually these are the problems that you're solving day after day, and they're usually on a similar set of inputs. So if you're doing a scheduling problem and you have to allocate jobs to machines, well, where did these jobs come from? It's often the case that this is the same job that runs every night. It's updating some spreadsheet somewhere, it's computing some allocation somewhere, it's updating a dashboard, it's doing something. And they're very similar, right? Or maybe some jobs run every day, but sometimes some machine dies or somebody forgets, somebody's on vacation, they forget to run it, whatever the case. So they're not exactly the same day after day, but my instance is very similar day after day, right? And so the question then becomes, how do I take my instance from yesterday and all of the work that I did yesterday to solve it, to say, can I do something faster today? I still want to be optimal. I still want to be the best, but can I just do it faster? So this is traditionally known as warm start in the OR community. It's the absolute thing that you must do. But little formal analysis is known here. And if we think to the kind of the algorithm side of things, there's a lot of algorithms that have a potential function argument about how they proceed, right? And we'll say, well, here's the worst case potential. We know that this potential reduces by some number every iteration. And so we know that the total number of iterations is either log, if it's relative, or just the division of those two, right? And those are a very good fit by saying, well, what if you didn't start at the worst possible case? What if I can prove to you that you started somewhere in the middle? Can you still then say, well, your running time is going to be shorter as a function of how well you got to where you needed to be, right? And this is where we're going to here, right? How do you decide what is that little part that you need to predict in order to make these kinds of claims? And what we're going to look at is min-cost matchings. Again, looking at very simple problems to develop our intuition a little bit more in this case. So bipartite graph, minimum cost matching. I have edges with some costs. I'm going to have a scale parameter that says this is the maximum cost over the minimum cost so that it's unitless, right? And my goal is to find the min-cost perfect matching. What's known? Right? Again, this has been known for a long time, at least the first couple of bullets. The computing max cardinality matching, here it takes about m root n time. And if you want to compute it in the weighted case, where you're not just looking at cardinalities, a lot of the methods use max cardinality as a subroutine. So the Hungarian algorithm, which is really what you use most often in practice, takes root n, at most root n calls to the subroutine before it converges. If you want to look at state of the art, you're going to use weight scaling. You're going to do other tricks. This is actually recent. It's pretty nice work. But you're going to pay an additional log c, where c is the scale invariance parameter. OK, so this is our bar. We're going to pay m root n kind of no matter what. But what we want to do is reduce how many times we call min-cost perfect matching. We want to reduce the term in front. Great. What do we predict? So you have the solution from yesterday. What should I do? So the first idea is to say, well, I have the solution from yesterday. Maybe I start with the solution from yesterday. And I'm going to run augmenting paths or whatever your favorite thing is on this solution from yesterday. This is not a formal proof, but this is a very brittle way to go about things, in that a very small change in the instance, however you measure small change, can lead to a very large change in the optimum solution. And so this kind of like, yes, you have the solution from yesterday, but it's too detailed. This is not what you want to go after, right? You're looking at the edges that were there and that were present. And so instead, what we're going to do is we're going to turn to LP duality. And this is something that's been used before in kind of similar settings that are not quite the same. And so what we're going to do is we're going to look at duals. So here I'm looking again at perfect matchings. The perfect matching's on the left, the dual is on the right, right? And what the dual says, I need to find shadow values or prices, these yi's, one for every vertex in my set, so that the sum of them is at most Cij. And complementary slackness tells me that exactly the edges on which these yi's, the sum of the two vertex shadow prices, is equal to the cost. Those are exactly the edges that are going to be in my matching. And this is how the Hungarian method works as well. It starts with these duals at 0, essentially. You compute a max cardinality matching on the tight edges. If it's the perfect matching, you're done. If not, you find a violator of the Hall's theorem, tells you a perfect matching should be. You update the duals and you go. And so what we're going to do here is we're going to predict a good set of dual values to start with. And we're going to say you shouldn't start at 0. That's throwing away everything you know about the instance. You know kind of what this shape looks like, which vertices are going to be more congested, which ones are going to be less congested. And so you're going to predict these y hats. You're going to predict these values. I'm going to call them by hats, right? And you're going to start there. And you can just run Hungarian algorithm starting there. There's one issue, and the issue is dual feasibility. Right? The Hungarian algorithm assumes that you start with a feasible dual, and you just slowly build it up, and you make it better and better. You make it higher and higher value, but you always maintain a feasible solution. The predictions, machine learning is machine learning. The predictions could be all over the place, and in particular, they're probably going to be infeasible. So the first thing that we need to do, right, and so they're infeasible if the sum is larger than the edge cost. So we want to reduce them as little as possible. We kind of want to project on the feasible polytope. So we're going to reduce these duals a little bit to attain feasibility. The reason that this is now going to be hard, or could be hard potentially, is that we don't have time to do this, right? We're competing, like we can't take quadratic time, we can't take anything else because we're competing on time with a basic Hungarian algorithm, right? Speed is of the essence here. But what is the problem that we need to solve, right? So here's the LP for it. But if you think about it, if you write it down and you stare at this, the problem is the following. You have a bunch of edges, right? You have a bunch of vertices. Every vertex has a weight. Some of these edges are violated in the sense that the sum of the weights of the vertices is too high. So what I want to do is I want to reduce the weights on the vertices so that the edges are not violated. And I'm going to do it in the following linear time greedy way. I'm going to pick a vertex that has a violated edge adjacent to it. And I'm going to say, OK, how much do I need to reduce the value on this vertex so that none of its adjacent edges are violated? And so I just scan through the neighborhood and say, how much do I need to reduce it? I'm going to reduce it by that amount. And I'm going to continue. Now, this is not going to give me the optimal solution here. There's a typo here. But this will give me a two approximation, not for the primal, but for the dual of this LP. And it's easy. It's just like vertex cover, right? Like that's why you get a two approximation. You have to pay at least this much. Yes, you might have to pay to fix a particular edge. You need to pay a certain amount. Well, you need to pay it either on the left or on the right. Maybe you're going to be smart about it. I'm just going to pay for it on the left, let's say. Okay? And so I lose this factor of 2 here. So what is the overall approach? Just to put it all together. We're going to learn or somehow obtain the duals. Maybe we'll use yesterday's duals. Maybe we'll learn them. We now have a new matching instance that somebody gives us. We're going to say, OK, I have these learned duals. I'm going to project them down to the feasible space for this particular instance. And I'm going to run my usual Hungarian methods starting with these learned duals. They're now feasible. And I can open up the analysis of Hungarian algorithm to say that you can start it in the middle. It doesn't really maintain any other critical invariants. And the running time, if I do this, is going to be, again, this m root n factor, which we'll agree we're going to pay. And now the number of times that I need to do this is the L1 difference between the predicted duals that I had, the original predictions, and the optimum duals for this particular instance. And so we get back to this nice category that says the better the prediction, the faster this is going to run. And what's not shown here, but you can sort of say, like, the worse the prediction, because the projection step is linear time, and afterwards you're, at worst case, you're left with duals of size 0, you're never worse than the vanilla Hungarian, right? And so again, you're just saying, like, well, if you have something to use, you can use it in this way. Right? And we also proved that the duals themselves are pack learnable. So it's not out of the ordinary to assume that you can actually learn these Y hats. That they exist, they're nice, they have nice structure, you don't need too many samples to learn. So this is the theory. It's relatively small. Yes?
There is a question. What do you mean, from Ola, what do you mean with no worse than vanilla Hungarian algorithm? Here, the hidden constants seem important. Otherwise, I could run both implementations in parallel on alternative steps. Or
yes.
am I missing something?
You're not missing anything at all. So right. So let me unpack that a little bit. Since we're doing running time, and I want to be kind of asymptotically no worse than an algorithm that I have, I can just run both of them in parallel, as Ola said, and whichever one finishes faster is the one that finishes faster. True, it's kind of unpleasant. Like, I would much rather have a single algorithm that I need to run and say, well, there's this projection step. It takes a little bit of time. And I'll show this empirically in a second. But if you ignore the projection step and the time that it takes, then at least you're not going to take more iterations than the Hungarian algorithm. You're stochastically dominate, if you will, the running time of the Hungarian algorithm per instance, right? And this is what you want to get to, because then you don't need to do these tricks. These tricks work in theory, of course. What's an extra factor of 2 on the running time? It's all under the big O. But in practice, like, that's costly. You don't really want to do this. But let me answer this also with an empirical thing. Does this work? Right. So the first one is going to be a synthetic set of experiments. And what we're going to do is we're going to say, here's a bipartite graph. I'm going to plant a min-cost perfect matching in it, right? And now I'm going to generate instances by just adding random noise to all of the edge weights. And so if I add enough noise, if the noise has very low variance, then one instance to the next, the planted matching should survive and should be the right thing to do. As I add more and more noise, I slowly get to just a random bipartite graph. And so learning should be useless and not give me anything. And this is exactly what we observed. So there's two plots. There's an orange line, which is on the bottom. There's a blue line that's on the top. The difference between the left plot and the right plot is just scale. The left plot is more of a zoomed in version of the right plot. And there's a couple of things to note. Like the first one is that when the first one's in the domain where the variance is low, so the noise is not that big. So when the noise is low, you do dominate starting from all zeros, or kind of some other heuristics that Hungarian uses. You actually use fewer iterations, and this is an iterations plot. The runtime plot looks exactly the same. So you are faster. You can save something there. The right plot says, okay, let's take this out and let's move the noise kind of more and more as we grow it. And we see these two lines converge. And once they converge, they also start growing linearly. And that's the time where you're really in random instance land. Right? There's nothing to learn. It's the same. You have to start from scratch from one step to the next. And that's what we're seeing here. If we do this, that was synthetic. If we derive perfect matching problems from geometric data sets, you see the same kind of change between what the learned predictions do and what the original Hungarian does. And some of the gains are substantial. And the final thing that I'll show is to say, here is a plot of the performance of the learning algorithm, where on the x-axis is the number of samples that I see to train and to say, what are my best predictions so far? And you see this kind of, it's noisy, but it's a slowly decreasing line that plateaus that says, initially, I haven't, my samples are useless. But as I go further, I learn something about the distribution, and I continue. And the number of samples, the theory predicts that I need n-cubed samples. Here I need like 20, which is usually the case. So to conclude here, as we slowly run out of time, the semantic problem that I want to attack is the fact that many problems are solved repeatedly, right? And how do I capture that to really use this repeated nature of similar instances to get a speed up overall? And how do I prove something of this? And I'm going to use this predictions framework, right? By really saying, here's something that you can predict. Here's something you can actually learn. It's pack learnable. And now I can use it to the algorithmic advantage. And the challenges are always the same. The challenges in all of this work is to say, what is the thing that we want to predict? It needs to be both predictable and useful, right? And those are the two things that we're balancing all the time. It's pack learnable, so I can predict it. I'm not just predicting the optimal solution every single time. That's kind of silly. At the same time, it needs to be useful, right? And so this forces us in a formal way kind of to identify the core of every particular problem. So that's it. There's more pictures of Alps. Many open problems here. I'm really excited overall about this area. I think we've only scratched the surface, even in the online algorithms case. We do have some number of results, but there's a lot of open questions there, both on how do you use them, what's the right thing to predict, how well can you predict certain things. And then the beginning of the talk that I started with by saying, can we use this as a way to really identify the core part of the problem to predict and really unify a lot of the analyses that we had before and say, here's one analysis that captures all of these things and that has kind of some explanatory power as to why we're saying the same shape of the solution in different problems. And with that, I will stop 1 minute early.
Thank you very much. So on behalf of everyone, thank you, Sergei. Are there any questions? Any suggestions, any improvements?
Please.
Any solutions? Okay. I don't see anything. So what for the secretary problem, if you have to choose more secretaries, would it be very different, or this would be
That's a good question. I don't know offhand. So if you're using K-secretary, I guess the usual formulations of K-secretaries have values, right? You kind of say, well, they're drawn maybe from some distribution or something between 0 and 1, maybe it's adversarial, and I want to get the metric that I'm competing with is the sum of the top K values.
I mean, the values might be the ranks.
The values could be the ranks, but they could be, I think
They could be auto-weighted, yes.
They're kind of a little bit weighted. So that becomes a slightly different problem. I have a feeling that similar machinery might work, but I'm not even sure offhand if, say, Bobby Kleinberg's 1 minus 1 over K algorithm fits in here. Like, how memoryless is it? I think it's pretty memoryless, so it should work, but I don't remember the details. It's a good question.
Or if you have a budget, you have, 100,000 to hire us. I mean,
right. Yeah, I don't know offhand. It seems like things would, like a similar intuition would work. I'm not sure the formalisms would go through.
Okay, here's a question from Robbie. Any further thoughts about what kind of info signal may be predicted rather than the solution itself?
So I think this is, the thing that we want to struggle with is to say, how do we capture the predictability aspect, right? Because that's the only way I know to kind of rule out this thing of, well, Sergei, why don't you just predict the optimal solution, then you'll be done, right? And the only tool here that we have is sample complexity from kind of pack learning. And so here I can sort of say, well, here's the solution space, here's the family of instances that I'm going to predict, here's what I can do. It's a little bit, I mean, it's reasonably well developed as an area, but it's still a little bit coarse overall, right? And so I can't really distinguish between if I get two different algorithms and says, here's two different signals, it's hard for me without kind of empirically looking at it to say, I prefer A to B, or the incomparable. So I think there's just more work to be done there, but that's the usual struggle of kind of like, how do you define learnable?
There is one more question from Sushanta. Do you believe that primal dual-based distributed algorithms can be augmented with this kind of dual learning strategies to get better results?
I think so. I think the insight from the last part is that a lot of these things seem to fall into the general proof structures of primal dual, right? Like this is usually what we do, where we have some objective function and we're trying to get them aligned, and we're increasing the dual and maintaining feasibility. So I think I think that's a very natural direction to look next. I'm excited about this topic, so that's why I'm talking about it before even it's on arXiv. But I think there should be something there. And then adding the distributed part to it makes it even better in some sense.
Okay, I think that these are all the questions. So Sergei, thanks again.